Okay, hello everyone. In this video, we'll be looking at a DFA building exercise where we're asked to create a DFA that accepts the language L, where all the strings in L are over the alphabet AB, and the number of A's in W is at most 1. So this notation means that the number of A's in W is or are at most 1. And we have an additional interesting thing to do is we're asked to also prove the correctness of the machine. Okay, so we need to prove that the machine we build does what we claim. Okay. And so this is just a good exercise to do once and then not much more again. It's good to see how you should prove correctness for one DFA, then the same idea kind of applies to all of them. It's just that they get more tricky and you have to just look at all the edge cases. But I think for our purposes, we'll do this example, and then most of the other exercises, I won't do a proof of correctness. But I think it's good for you to know what that would look like. Okay, so, well, let's do the first thing, right? So let's say that this is the first part and this is the second part. The first part of the exercise is actually building the DFA. Okay, and that turns out to be probably the easiest thing about this exercise, because if we want to build a DFA that accepts strings with at most 1A, essentially what you want to do is you want your DFA to keep looking for A's, and as soon as it sees more than one, it starts rejecting anything else, right? So what that means is that my start state Q0 is going to be an accept state, because I do want to accept the empty string, right? So I want to accept the empty string because the empty string has no A's, so it definitely has at most one A. Okay. Then if I see B's coming, I'm still going to stay here, right? So what I'm doing essentially is I'm encoding having at most 0 A's. So in fact, I'm encoding having number of A's equal to 0 in the state Q0. Okay, so what I mean by that is that the state Q0 is responsible for gathering all the strings that have 0 A's, right? So all the strings that have 0 A's are either the empty string or any number of B's in a row, right? So you can imagine if I have the empty string, I say in Q0. If I have BB, this should be accepted, and so I just stay in here. I'm like waiting for a first A, right? Once I get this first A, I transition to another state. Let's call that Q1. Q1 is still going to be a final state, or an accept state, because at this point you've seen 1A, right? So you've seen 1A, which respects the condition that your string should have at most 1A. Okay, and so really what Q1 is doing, Q1 encodes having the number of A's equal to 1, exactly, right? And now, so you can imagine maybe you had BB, right? Maybe you had BB, then you saw your first A, so now you're at Q1, and now you could see more B's. That's not going to change anything, right? So if you see more B's, you're still going to stay in Q1. You're still going to want to accept, okay? But now, as soon as you see another A here, then you want to immediately start rejecting anything else, right? So as soon as you see another A, right, this means that at this point, you have seen two A's, right? And so now this condition is violated, and so you want to reject anything else, okay? And so once you go to Q2, Q2 is just going to be a dead state. So anything else that you see at Q2 is going to be rejected, okay? And so what I claim is that this machine here that I just built, so I claim that this machine here, let's call it M1, okay? So now my claim, okay, so my claim is that the language accepted by M1 is indeed exactly equal to L, right? Where L is what we actually wanted to accept, okay? And so typically in most exercises, I would end the video here, but now what I want to do is I actually want to prove this, okay? So that's going to be the second part of the video, where I'm going to prove the correctness of M1. And so you might have created a different machine, okay, that would have accepted the same language. And so in that case, your proof of correctness would look slightly different, okay? Each proof of correctness for DFAs looks different based on the machines because each machine has slightly different mechanism, right? But the ideas on how to actually prove the correctness remain the same, okay? And so how do you do this, right? You do this by double inclusion, right? So each of these two things, right, the language accepted by M1 and the language L, both of these are sets of strings, right? And I'm claiming that these two sets of strings are equal. So what I need to do then, right, and so then to do this, I need to prove that the language accepted by M1 is a subset of L, and L is a subset of L of M1, right? And so what are each of these two things saying, right? But what does this actually mean? Does this mean? Okay, so first of all, this direction is saying, if I say that L is a subset of L of M1, okay, this is saying that any string in L is accepted by M1, okay? So that's one direction. This doesn't necessarily imply that the languages on the left and right are exactly the same. Why? Because M1 could accept everything, right? If M1 accepts everything, then of course L is a subset of L of M1, right? So that's why you need the other direction, which I'll talk about in a second, okay? So that's why you need the other direction. So L of M1, subset of L, is that any string accepted, right? Any string accepted by M1 is in L, okay? So you need both of these things to be true, right? You need both of these things to be true so that the language accepted by M1 is exactly equal, right? Is exactly equal to, that the language L is exactly equal to the language accepted by M1, okay? And so how can you prove this? Formally, if you want to do this very, very formally, right? To prove this formally, okay, you can use induction, okay? And you're going to use induction on different integers in both directions, okay? So in the first direction, right, so let's say this is direction A, this is B. So for A, what you want to show, okay, is you want to show that any string in L belongs to the language accepted by M1, right? And so what you can do is you can prove this by induction on the length of the string in L, okay? So where your where your inductive statement, right? So where the statement that you actually want to prove, so that your inductive statement would be something like any string of length n in L is accepted by M1. Okay, so this is how you would do it formally. You would set up this induction, and you would have the base case, right? So what are the smallest strings in L that are accepted by, what are the smallest strings in L, right? And then show that they're accepted by M1. Then assume that any string of length n in L is accepted by M1, and then prove in the inductive statement that any string of length n plus 1 in L is accepted by M1. That would be your goal. The other way that we can do this, which is a bit more intuitive, is just understanding what strings in L would look like, and then seeing if the machine M1 actually accepts those strings, right? So this is to be very formal, right? The other way, which I think equally works, is, right, you can characterize the strings in L and refer to the transition function of, in this case, your machine M1. Okay, so what I mean by that, and this is what I'm going to do here, right? So if a string is an L, right, and now I'm talking about this particular L. So I'm talking about this L in particular, right? So if W is an L, right, then the number of A's in W is either 0 or 1, okay? And so if the number of A's in W is 0, that means that the string is either the empty string or it's a bunch of B's, right? Okay. But then if this is the case, right, in this case, the string will remain in Q0 of M1, right? So if you have no A's, your machine, the way that it's built, its transition function is made so that it always stays in Q0 if there are no A's, right? And so since Q0 is a final state, M1 accepts all these strings, right? And this is a perfectly acceptable reasoning. You might think that the induction is a bit more rigorous. I guess it kind of is, but this is just as waterproof, in my opinion, as an induction proof. Okay, it's also much more intuitive and much less mechanic. Cool. Okay, so what if the string has instead 1A, right? So if it has 1A, that means that the string looks like some B's and then an A and then some B's. So here you could have, it's possible that you could have no B's, or possible, but you definitely have 1A at some point, and then you have some more B's, or no B's are possible, or no B's are also possible, right? But now in this case, if we look back at our machine, in this case, that means that, maybe I have B's, maybe I don't, so I stay in Q0. Then I definitely have an A, so I transition to Q1, and then maybe I have B's or I don't. But that definitely means that at the end of reading the string, M1 ends up in Q1, which is a final state, right? And so in this case, the string will always end up, let's say, in Q1, which is a final state. Therefore, M1 accepts all these strings. Okay, so essentially what I've done is I've split the language L into cases, and then I've shown that in any case of what my string looks like, this string is going to be accepted by the machine. Okay, so that's how you would prove formally this first direction, A. Okay, so how would you prove the second direction? So again, you can do this two ways. You can either use induction, and in this case, right, in this case, if you do by induction, then the idea, if you want to show that any string accepted by M1 belongs to L, you want to use the mechanism of the machine, right? So you need to use the mechanism of the machine, right? And so the mechanism of the machine is the transition function. Okay. Based on what the machine is doing, you want to show that whatever the machine does, if it accepts a string, that string has to be an L. Okay. And so then what you need to do is, if you want to use induction, this time on the number of transitions. N that M1 takes. Okay, and so more formally, the inductive statement would be any string. So let's see. Right, would be all strings accepted by M1 using n transitions, right? So n transitions is not the right term, n number of transitions belongs to L. So what I mean by that, okay, so what would this look like if I quickly redraw the machine here? So if you read a B, you stay in Q0. If you read an A, you go to Q1. And if you read more Bs, you stay in Q1. If you read another way, you go to Q2. Okay, so in your base case for this induction, right, you take all these strings that are accepted by M1 with the smallest possible number of transitions. In that case, in this case, for this machine M1, n would be 0, right? This is the smallest possible number of transitions for which M1 accepts a string, right? So when n is equal to 0, the only possible string, in fact, is the empty string. So M is accepted by M1, and the empty string happens to belong to L, right? Then in the inductive hypothesis, you assume that for every string in the language accepted by M1, such that delta star Q0W takes n transitions, right? So in other words, this is for these machines, right? So for DFAs in particular, this is equivalent to meaning that your string has length n. Your string has length n. But we'll see when it comes to other mechanisms like grammars, this isn't necessarily true. So you could have more than one step for your grammar, and you won't have a different length for your string, right? So essentially the number of steps in a grammar aren't bijective to the length of the string, but that's a whole other story. Okay, in this particular case, right, for DFAs, if I'm saying that the transition function takes n steps, it also means that the length of the string is n. Okay, and then in the inductive step, you need to show, right? So you would want to show that any string accepted by M1 such that the transition function takes n plus 1, so takes n plus 1 transitions. The string W is an L. Okay, and so how you could do this, you could just break down, you would break down W into some string V, right, of length n, and then some letter sigma, right? So sigma is some letter in the alphabet, which in this case is AB. Okay, and then you would need to break up based on where your string W ends up. You would have to split that into cases, right? So you would split into cases for delta star Q0W, either in this case can go to Q0 or to Q1, right? In both of these cases, you're going to accept the string, okay? And then argue what it means then for the string W to be actually a concatenation of a string V and sigma. So then what you need to do is you need to analyze the transitions that are possible with the string V, okay? So then analyze based on this, right? So based on this transition, what delta star Q0V could be. And it's at this point, right? And at this point, we can use the inductive hypothesis, right? Because now we have a string V of length n, okay? And so if we have cases where V, when read by the machine M1, ends up in the final state, then we have the recipe, right? We have the if condition for the inductive statement, right? Because we'll have a string of length n, so n transitions, and we'll know that V is also accepted by M1, right? So, right, at this point, we can use the inductive hypothesis for the cases where delta star Q0V ends up in a final state, okay? And so here, this might be easy to do, but in more sophisticated cases, you have to think a bit more about what states can V end up in? Well, what states can M1 end up in when reading V? Okay, and then analyze how to use the inductive hypothesis in that case. Okay, and then finally, what you do, right? So finally, by using the inductive hypothesis appropriately, you would conclude in some or all cases, you would conclude that V is an L, right? And then what you have is you have the string W is equal to V, which is an L, and then you have some letter sigma, which is in sigma, okay? And you have to argue based on where your machine ended up in when reading W, what this sigma could be, right? So then based on what sigma could be, you would argue that the whole string W is an L. Okay, so this is how you would do it for, this is how you could do the induction for this direction. Okay, I've essentially done a sketch of how you do it for this particular machine, but this is how you could do it also for any general machine. So this is one way. I think another more intuitive way, right? So another alternative, you can do it more intuitively by breaking up where your string ends up in, right? So break up cases of where M1 ends up in, right? So it's a machine that ends in a state. So in this case, if I have some string in L of M1, this means that delta star Q0W is an F, which means that it's either in Q0 or it's in Q1. So if delta star Q0 is equal to Q0, then this must mean that W is just a bunch of B's, right? Which is definitely an L. Or it could also be the empty string, right? Which is also definitely an L. Or you start at Q0 and you read a W, you could end up in Q1, which means that W has exactly one A. And so any string that looks like that is also an L. Okay. And so that's how you could do it more intuitively. This works in this particular machine, but in more complicated machines, sometimes it's not really possible to do this intuitive argument. And so that's when you have to resort back to doing an inductive argument like this. Okay? And so that's how you would prove the correctness of this machine. So you can see we took up this much space to actually build a machine, and then all this space to prove correctness. So quickly, just to recap, A, I said you could do either by induction, again on the length of the string in L, or you could also characterize the possible strings in L and then refer to what your machine M1 could do. In the second direction, when you want to show that the language acceptable by M1 is a subset of L, you could either do this by induction on how your machine actually works, so using the number of steps that your machine takes, the number of transitions, or you could also do it more intuitively by saying, if your machine M1 accepts W, then that means that when reading W ends up in some specific set of states, namely the final states. And then based on each final state, you can characterize what your string would look like. And then you could argue that for each characterization, the string would also be an L. Okay, excellent. So that's how you would build the DFA and then subsequently prove correctness.